Hello everyone, today I will be presenting our final machine learning project focused on analyzing and modeling carriers list card listing. This project covers dataset injection, preprocessing, EDA, dimensionality reduction, feature importance, and final conclusion. Uh, uh, Dataset overview, like a dataset is sourced from carriers list vehicle listing across the United States. uh, EDA like vehicle age versus price. Here we examine how price varies with vehicle year. While newer cars tend to be more expensive, extreme outlier inflates the upper range. You will notice the billion dollar price clearly erroneous entries which influence the decision to apply transformation and clipping later. uh, Mileage versus price. Mileage is a strong negative indicator for price. Higher mileage usually means lower price, but again extreme outlier break the pattern because some very high price listing have inconsistent mileage. Median price by manufacturer like Ferrari, Aston Martin, and Tesla dominate the top of the price distribution. And vehicle type, talking about the vehicle type, a difference vehicle type shows clear difference in a median price. Pickups and SUVs generally tend to be higher. Vans, hatchbacks, and sedans shows lower price variations. uh, Price by condition, as expected, new and like new vehicles show higher price. However, outliers exist even in a categorical like salvage, demonstrating the noisy nature of the real world scrap data. Transmission versus price, or transmission versus price, and fuel type versus price. Automatic vehicle dominate the data set. Uh, Manual car do not show higher price on average, which goes against some market assumption. And electric and hybrid car tend to show higher median price. And color versus price shows color suppressingly shows almost no predictive power. There are many outliers, but for most color the distribution is flat. Median of price by state. uh, Certain states like West Virginia and Alaska show much higher median price. This is like a due to smaller dataset size or outlier influence rather than genuine market effects. Regression insights. Uh, Transforming both price and mileage using log 1p reveal a much more stable pattern. The regression line shows a weak negative slope, but the R2 remains low. This confirms that the simple linear relationship is insufficient, motivating use of more flexible model like neural networks. Talking about the linear regression or regression insights. Filtering to year greater than equal to 2000 reduces noise. We observe a slight upward trend, newer vehicle, higher price, but again linear regression cannot capture the full complexity. R square is extremely low, showing weak linear prediction. And year versus price lowness. Uh, Here we compare the flexible lowness trend curve to the linear model. Lowness low is clearly fit the data better, especially after 2010.
We evaluated 6 classification models to predict whether a car is expensive or not. Random forests perform the best with 94% accuracy, high precision, and high recall. Logistic regression and gradient boosting were moderate, while KNN and MLP struggled with recall. Overall, ensemble models clearly outperformed simpler models. Confusion matrix insight. This confusion matrix shows random forest performance. Both true positive and true negatives are very high, and false predictions are very low. This means the model rarely mislabels cars and captures most expensive vehicles correctly. Its precision and recall make it highly reliable for real world classifications. Final conclusion. Random forest is the best choice for this project. It gives the highest accuracy and balanced performance across all metrics. Other models help us compare behavior but non-match random forest stability and predictive power. So our final recommendation is to adopt random forest for vehicle price classifications. Data cleaning and feature engineering. All we did was remove outliners, handle missings, and engineered features. Hyperparameters. The best performing model achieved improved RMSE after applying long transformations and feature engineering. Simple linear regression performed poorly. Neural networks and tree based models performed significantly better. Dimensionality reduction was used to visualize high dimensional relationship. PCA captured global variance but could not separate vehicle categories. TSNE and UMAP produced clusters that corresponded loosely to manufacturers and price brackets. These visualizations helped confirm redundancy in several categorical features. Technical challenges. The dataset contained extreme noise, mislabeled entries, missing values, and impossible prices. Preprocessing required imputation, clipping, long transforms, and category consolidation. Modeling challenges include overfitting, high variance, and inconsistent features importance. Computational cost was significant due to dataset size. Conclusion and future work. In summary, car prices on Craigslist depend mostly on year, mileage, manufacturer, and type. Neural networks and tree models outperform linear methods. EDA and regression reveal strong non-linearities and heavy tail distributions. Further improvements include advanced outliner detection, better text feature extraction, and geographical normalization. Thank you.